Hello, I'm Christopher Bentley, a senior quantum control engineer at Q-CTRL, and I'll be presenting our work on fast, noise-robust pulses for parametric entangling gates in superconducting qubits. Our colleagues at Rigetti also contributed to this collaborative work and presentation. Quantum computing offers a fundamentally different computing paradigm than classical computing. This quantum paradigm offers exponentially better resource scaling for solving important problems, known speedups in others, and great potential for still broader application. Superconducting qubits in particular are a world-leading platform for quantum computing, and access to these systems has moved out of labs and throughout the world through cloud access to systems like that in the schematic shown from Rigetti. Nonetheless, challenges still remain in this era of noisy intermediate-scale quantum devices, as noise sources still impact the quality of computing operations or quantum logic gates, and thereby limit the capabilities of algorithms on real hardware. In this presentation, we apply Q-CTRL's expertise in quantum control engineering by optimizing and modulating control pulses to improve the robustness of parametric entangling gates. These gates are employed as entangling operations, a computational building block on Rigetti superconducting qubits. So what are parametric entangling gates? These are a form of 2-qubit quantum logic gates that can be used to provide an entangling operation in quantum circuits for computation. Consider 2 superconducting transmon qubits, one with a fixed frequency denoted by F and one with a tunable frequency denoted by T. Both qubits have transition frequencies, which are depicted by solid lines on the slide. The 0 and 1 levels can be used as logical qubits, and the 0-1 transitions are marked. The 1-2 transitions for each qubit are also shown, where 2 is an auxiliary energy level, and the 1-2 transition has lower frequency than the 0-1 transition due to the anharmonicity of each qubit. To generate interaction between these qubits, flux modulation is applied to the tunable frequency qubit, which modulates the transition frequencies in time. So we have shown the average transition frequencies denoted by the bar over the F. The average frequency is then dressed by sidebands, shown as red dashed lines, which are spaced by the modulation frequency. When the modulation frequency is carefully chosen, this produces an effective resonance interaction between the 2 qubits. Then current exchange occurs such that population can move between the 2 qubits. For a particular choice of the modulation frequency, coherent exchange occurs between the 1-1 and 0-2 states, and here the effective resonance is marked by the gray line. By tuning the length of the flux pulse, population can be transferred out of the 1-1 state to 0-2 and back again, inducing a pi phase and performing a CZ gate. To compute with these gates in practice, we need to be aware of the noise processes that impact their performance. Flux noise can significantly reduce the fidelity of parametric gates. However, AC or dynamical sweet spots have been derived and demonstrated, which render the gates first-order insensitive to 1-on-F flux noise. In the top plot, the average transmon qubit frequency shift induced by modulation is shown, and the turning point can be observed where the flux modulation amplitude is at 0.6 on the x-axis. The frequency shift is first-order insensitive to flux amplitude changes at the turning point, giving rise to the gate insensitivity. The dephasing timescale is shown in the lower panel over the flux modulation amplitude. At this 0.6 amplitude dynamical sweet spot, the dephasing timescale is around as high as when no flux modulation is applied. The paper shown by the Rigetti team demonstrated high fidelity gates by making use of this dynamical sweet spot. In this presentation, we will be looking at moving from a sweet spot to a broader, robust regime for parametric gates. Note also that replacing a single frequency flux drive with bichromatic modulation can be used to engineer properties of the sweet spot. And you can check out the talks and the paper by our colleagues at Rigetti for more information. The dynamical sweet spots that we've been discussing arise at turning points of the tunable qubit's average frequency, as for instance shown by the white dashed line in the left plot. The resonance conditions for the flux modulation frequency also depend on the tunable qubit's average frequency, which is shown in the color scale of the left plot. Here, the flux frequency and amplitudes corresponding to CZ gate resonance conditions are marked in red and blue dashed lines for two different transitions. The dynamical sweet spots are at the turning points of the resonance condition curves. This can also be observed in experiment. The right-hand figure shows half a CZ gate where population has been transferred out of the 1-1 state when the resonance conditions are met. For flux noise robustness, we look at the turning point or the curve of the boomerang to find the sweet spot. Typical parametric gates involve pulses with fixed frequency, amplitude, and phase, as shown here in blue. Scanning the amplitude and frequency in experiment for half of this pulse lets us see the effective population transfer regions out of the 1-1 state that we require for a CZ gate. There is a very small region depicted with a pink point corresponding to the robust sweet spot. A key question here is, can robust solutions exist outside this tiny parameter region? At this point, we introduce modulation of the applied flux pulse, which can be optimized to improve robustness. On the top left, you can see an optimized flux pulse envelope, where the phase is modulated over time within constrained limits for pulse smoothness. We introduce here a robustness infidelity measure to assess the robustness of the optimized gate. The infidelity of the optimized pulse is added to the infidelities obtained by increasing and decreasing the pulse amplitude by 4%. Using this robust infidelity measure as a target amounts to a simple grid-based optimization for flux amplitude robustness. The figure in the bottom left demonstrates, first, that a broader range of gate durations can be performed with amplitude robustness by using phase modulation, and second, that the breadth of the robust region is increased slightly for the optimal duration. The robustness infidelity is slightly improved for the best gate duration. On the right-hand side, varying the frequency and amplitude of phase modulated pulses can be observed in experiment to transform the shape and location of the sweet spot on the boomerang curve. Amplitude modulation can be used with similar effect to phase modulation. But can we have still more control over the robustness region? Let's now add in single qubit drives for the 2 qubits, where the I and Q components for an example drive with a fixed maximum Rabi rate are shown on the left. And for simplicity, both drives are at the transition frequency of the fixed frequency qubit. Applying these drives in combination with a flux pulse greatly increases the breadth of the robustness region for different pulse durations, seen by the lower infidelity measure at each point. And it also allows a much broader range of gate durations, and thus faster gates. These gates still retain flux amplitude robustness. When we have the additional control knobs provided by the single qubit drives, we can also introduce robustness to different noise sources. Here we show that adding the single qubit drives greatly increases robustness to ambient dephasing noise. This can be seen in the left-hand figure, where the flat, low infidelity region shows the robustness provided by these controls over a quasi-static scan of detuning for both qubits. Filtering the controls to produce smoother drives, as shown on the right-hand side, reduces the available control and thus reduces the robustness to dephasing noise, depending on how much filtering is required. Here, very high-powered drives with maximum Rabi rate of 100 megahertz are applied, but the same effect can be shown for lower powers. Through this presentation, we have seen that robustness is critical for high-fidelity parametric entangling gates. We can enhance robustness to flux noise, which is provided by dynamical sweet spots through modulation of the flux control. We can further enhance this robustness by adding single-qubit drives, which can additionally be optimized to provide robustness to other noise sources, such as ambient dephasing noise. Furthermore, the combined flux and single-qubit drives enable faster gates than those performed just with flux control. The next stage of this work is to apply these optimized flux and single-qubit controls in experiment, and to quantify their performance and robustness on the chip. We're very excited to see where that will take us. Thank you for watching this presentation from Q-CTRL and Rigetti. If you have any questions, you can reach out to us by going to qcontrol.com or rigetti.com.